Hi, I'm Dr. Mike Brofchek, the Loy and Edith Harris Assistant Professor of Computer Science at the University of Wyoming. And in this first video, I'd like to talk to you about what is computer science. But first off, this video is made possible by funding from the National Science Foundation under a Research Experience for Teachers site grant called WySTACK, supporting teachers and computing knowledge. By the end of this presentation and the associated video, we hope that you'll be able to explain the difference between computer science and programming, recall several characteristic domains of computer science, recognize differences between some of the computing disciplines. We also hope that you can define 4 major things that every computer does, recognize the major features of programming languages, and execute some of your own code. Now, we recognize that you won't be able to do this as an expert from memory, but hopefully as a learner with some additional resources. So with that, let's look at the biggest misconception about computer science. And that is that programming is computer science, or that computer science is programming. Neither of these statements is true. These statements are as true as saying chemistry is pipetting, or mathematics is plotting numbers, or flipping those around and saying plotting numbers is mathematics, pipetting is chemistry. That's generally something that we all can understand is not the case. So why is it that there's such a misconception about computer science and programming? So, I'd like you to take a moment and think about the general subjects you teach. What are some misconceptions about those subjects as a whole? Not individual misconceptions within that domain, but what are misconceptions about perhaps what somebody with a biology degree does, or somebody with a mathematics degree? What are misconceptions that perhaps the public has about those subjects and what you can do with a degree in those subject areas? All right. So, if computer science is not programming, what is it? Well, computer science focuses on scientific and mathematical study of computing systems, computations themselves, and computing processes or algorithms, the instructions that we use to tell a computer what to do. Consider a laboratory or real-world measurement of some kind. So, graduated cylinders here on the right. Different systems have different characteristics, different capabilities, efficiencies, ideal uses, precisions. The same holds true in computing systems. Your smartwatch has different characteristics and capabilities than perhaps an iPad or a laptop. These things also have different capabilities than perhaps the computing systems that are in the Mars rover, or in the space shuttle, or in some other device. How we utilize our systems, how we organize instructions, how we extract information also has many impacts. So using the right tool for the right job, very important in all disciplines, including computer science. We would like to study, and we do study, the impacts of these different systems and different techniques throughout everything we do. Another thing to maybe look at or to consider when trying to think about these distinctions, if we were to add 3 numbers together, let's do 3 plus 3 plus 3, it clearly yields the same result as 3 times 3. Both of these are mathematical operations. The question is one approach better than another at yielding the result we're looking for? Is one more universal? Is one easier for everybody to be able to do? Is one more efficient in terms of time? Is one less complex, let's say either mentally or time-wise to compute? So is one of these approach better than the other? What metrics are you using for comparison? All of this is important, and we use these same ideas throughout computer science. So, now why is there such a misconception? Well, computer science studies how to solve problems using computers, while programming or coding focuses on the actual implementation of those solutions. Computer scientists can, and most often do, use programming as a tool to implement their solutions. So, when we talk about computer science, programming and coding is often utilized, but there are a handful of famous computer scientists that have not once programmed. It's unusual, but it's not unlikely. So with that, what are some of the major domains in computer science? And so to do this, if you asked 100 different experts, you would probably get some variation in answer. So what I've done is I've utilized the Wyoming State CS standards as a baseline. These are pretty good segmentations, but just know that they are not universal. So on the one side, we have the systems that we're going to use in computing. So these are the physical devices that actually perform the computations we care about, perform the actions. Next, we have how are these computing systems connected, the networks of these systems. Next, we have, I'll say, a very broad area of what happens, of the use for computer science, and most of it actually ends up being focused on data analysis, which has huge connections throughout most of the STEM disciplines and beyond. But talking about the manipulation and extraction of information and meaning from data. So hopefully you'll see that has a very clear connection to a lot of, like I said, your STEM disciplines. Finally, we move into what most people view as computer science. We've mentioned it's not squarely here, but it's in the development of algorithms and the actual programs themselves. So algorithms are your set of, I'll say not the instructions themselves, but the process. How will you solve the problem? So the algorithms are the how, and then the programming is the actual set of instructions that are used. So design, analysis, and actual implementation of solutions. And then finally, all of these things put together have massive impacts on the future of society and really the future of all things. So what are the impacts of computing is another area, another domain within computer science that warrants a lot of study. I've put a link here to the Wyoming State Standards for Computer Science, and that QR code should also link you there as well. So with that, let's start diving in. What is something that every useful computing device do? So what is something that they all do? They all capture some type of input. They all store data of some kind. They all process data, and they all produce output. Now, you might find some very specific types of systems that might omit one of these steps, but it's unlikely, and in terms of being, I'll say, generally useful, that would be unlikely as well. So, by that definition, you are a computing device. You capture data through your senses. You store data within your memory. You process data, thinking. Anytime that you are extracting meaning, anytime you are transforming information, you're processing data. And then you output data as well through communication of some kind. You might also output data and store it internally, right? A nice example is talking to yourself, reflection. All of these are processes where you're outputting information, outputting data back into yourself. So, just like we humans can capture, store, process, and output data differently, the same holds true for computational devices. The reason why computer science exists as a discipline is that there are many different ways of solving problems, many different ways of capturing, storing, processing, and outputting data. And a lot of our time is actually spent on the processing step, but all phases require attention. So, with that, how do we actually get a computational device to do things, right? So we have devices. How do we actually get them to do anything at all? So, well, it's simple, in quotes. We tell them what we need them to do. So a modern computer, though, under the hood, you peel everything away, is nothing more than switches that represent 0 or 1, true or false states. We're not going to get into all the complexities of how that works, but you have to understand that under the hood, we're just talking about controlling some bits. And we're going to do this in high-level ways, but before we get there, let's imagine that this is our computer, 26 light bulbs, and I want to share the word hello to someone. Can you come up with a set of instructions that would get somebody else to send the word hello? So I'll give you a moment, pause the video if you'd like, and try to write down just a set of simple instructions on how you might have somebody send a message, in this case hello, to someone else using these 26 light bulbs. I'll give you a moment to hit pause. All right, welcome back. So, an algorithm is just a sequence of steps that, when followed, should convert input or some data that you have from one form into another. So, in this case, we want to send the word hello. So one potential algorithm could be take the word or string of characters and work on one letter at a time. For each letter, in the order that they appear in the word, you could convert that letter into its corresponding letter in the alphabet. So if A would be 1, B equals 2, C equals 3, all the way, so on and so forth, until Z equals 26. You could then take the corresponding light bulb and turn it on for 5 seconds, then turn it off. And you would basically repeat this for all letters that you have. So what you would see if you were observing this set of lights is you would see light turn on for H, corresponding to the correct number, then E, then L, then L, then O. Okay, that would work. So could we maybe be a little bit more efficient? Well, we could maybe create a cheat sheet of words. If a word exists in the list, just turn on the corresponding bulb, right? So maybe we send hello a lot, so hello would be in space 1. We just turn light bulb 1 on, and we've just sent hello out to everybody. Okay, well, that's great if the word exists in lists. So how could I do that? Well, if I had my list and it was completely blank, I would have no way to send out the word hello or any other word. So what I would do is I would blink all the lights at once to let the person, whoever I'm sending the message to, know that I'm about to send a brand new word. I would be, if this is my very first word, it would be in spot 1. So I'm going to write that down in spot 1 for me. Blink all the lights, turn on the light bulb corresponding to the number that I just noted. So I'm going to turn on light bulb number 1, 10 seconds. It's going to let the other person know, hey, I'm about to send a new word, and it's going to be stored in our first item on the list. And then we could send the word as we described earlier. So basically, the other person will now know, hey, in my cheat sheet, here it is. Hello will be word 1. And that is another way that we could maybe make things more efficient. So just something to consider. So let's do a little aside on efficiency. Is this efficient? 26 letters in the alphabet, 26 bulbs, 1 bulb per letter. This is actually a common encoding method for data. 1 bulb per letter or 1 bit per element. But what if we arrange things as a grid? Now I understand there's 26 letters in the alphabet, and a 5x5 grid has some issues. One letter would have issues. In this case, it's I and J. But this is actually a common encoding technique in a lot of security mechanisms. So here we go. We have 10 bulbs now. So we've cut our bulbs down drastically, but now we require 2 bulbs to share each letter. Okay, could we do any better? Well, on the right hand side, we could use 5 bulbs, and we would have to look at all the states of all the bulbs, but we could represent our 26 numbers, which correspond to each letter in the alphabet, down to a binary representation. We don't need to get into decimal to binary conversion today, but we do need to understand that how we encode data matters. Even though we're efficient at storage, it's a trade-off decision, right? If now I have to encode and decode my information, that takes time. People need to understand my encoding. So, all things to consider. So, let's get back to telling this computational device what to do. Clearly, we're not going to be turning on light bulbs or individual switches in our computer. But, historically, it did mean that we would have to write machine instructions. So, if you look at the diagram on the left, the picture, writing specific machine level code used to take some expert knowledge of the device you were programming for. Over time, we've gotten better, and today we use high level programming languages, which let us write things in human readable syntax, which then, by the way, get translated to machine level instructions. So if you want to check out a collection of over 600 Hello World programs, which is the kind of the default of seeing a brand new language, check out the collection that's there. And I will also mention that some of these high-level languages aren't necessarily human readable. So the picture on the right with the alternating red and blue squares is actually a language called whitespace, which is entirely written using tabs and spaces. Not something that any of us wants to do today or anytime in the near future. So, something to ponder. Why do multiple programming languages exist? So, programming languages ultimately enable us to input data, store data, process and operate on data, and output data. And basically all these languages contain keywords and use their own syntax to enable programmers to create instructions. All of these things line up very nicely to what a computational system, a device, can do. Imagine that these are human tasks. Input and output can take many forms, but how we gather information and communicate is relatively straightforward, right? There's room for differentiation in how we communicate, but realistically, there's a few ways that humans communicate. And those are easily described. Storing data, we have some already fixed constructs as humans in terms of we have alphabets, grammars, mathematics, number systems, which have changed, by the way, over millennia. And then there's processing of operations. This is where there's huge regions for, I'll say, differentiation amongst us as humans. So all I'm getting at here is that in computing it's very similar. There are some fixed instructions for how to input and output data. There are some fixed ways for how do we store data and what we might be able to do to manipulate it. But in terms of how do we put all of the processes together, the algorithms, the individual steps, there's huge rooms for differentiation. And so our languages that we have, our programming languages, have to be able to support this. So different languages have different benefits and uses. And the biggest discriminating factor is the use case. Where is my code being used? If I'm doing something in one space, I'm going to use one language. If I'm doing it in another, I might use a completely different language. So found this image online, and you can also do many searches for this. This is a common question. What programming language should I learn? And so this particular author for this flowchart does differentiate between certain spaces. All you need to know here is that depending on your end application, you might be constrained by a certain language. Now, one of the languages that is very wide open that we're going to be using just as a learning space is Python. So we're going to use Python 3 in this intro to CS. And what we're going to do this week is we're going to focus on output, input, storage, and basic math. Now, I know that seems like a lot, but it's actually just 2 really quick lessons. And because this is meant for a self-guided research experience, we're going to have you head over to sololearn.com, create an account, and go with the Python core course. I want you to complete the first 2 units. And when you're running the try it yourself examples, I want you to try adding in new code statements and explore the concept. Don't worry about breaking things. This is really just an exploration. You'll also take some of the things that you're doing in SoloLearn and translate it into our Replit space. So if you take a moment, like I said, head over to sololearn.com. And also, if you'll join our Replit account, so you can go to YCSX.org/WYSREPGEN, and that should lead you to an ability to log in to our Replit account that will connect you to us. And what you're going to do is you're going to put a few things in there. So let me quickly switch screens here and show you where you're going. So here is sololearn.com. And if you go to the menu at the top here, this might look slightly different. Let me open it. Let me make it a little bit bigger for you. If you don't have an account yet, you can register. It is completely free. And when you are registering, you can select one of these, but you can also do this later. We're going to just do Python Core, and you'll see that there's already 7.2 million learners for Python Core. Sign up. It is a lot easier if you just sign up with Google account if you have one, but you don't need to. So let's see if probably won't let me sign up a second time, but let's see what happens. It might tell me I already have an account, but that's all right. You do not need to upgrade to Pro. All right. And here we go. So apparently I did not have an account with that username, which is great. So you'll be able to see exactly what this looks like. So you're already in. You might get an email asking you to confirm your account. But what you're going to do is you're going to run through the basic concepts and the strings and variables units. All right. So what happens when you go into these lessons is there's a mixture of essentially try it yourself code. So you get some introduction. Don't just click try it yourself. Actually take the time to read through these. So click on try it yourself, and it will actually bring up essentially a live environment for you to code. So the code you write on the left will execute and print out or display on the right. So when you click run, you'll see this is working, and you get a hello world. Just for a test here, hello world YCS, just so you see that there's a change. And it's not just some faked system, and you see the output here. Now if things break here and you try to run it, you will get errors. This is a fully functioning environment. So once you've tried the code yourself, or if you get to a state where things are completely broken, you can always go back. So the X in the upper left hand corner lets you go back. You don't have to save things if you don't want to, but you're definitely welcome to. So trying it yourself is great. You can, for some of these, you'll see the option to run code as practice. Now that won't be enabled for all of these, but it is for many. All right, so as you continue going through, you'll have some opportunities to check your understanding through various drag and drop mechanisms or fill in the blank. Go through, do the activities, try the code yourself, modify the code, make sure you understand what's happening, and ultimately you'll reach a point where there'll be an end exercise. So let me show you what that looks like and what you're going to do with it. So let me log out here and go to another account that I know should have access already without showing you all the answers. So at the end of each unit, is a project. When you get to the project, you'll basically have a long explanation, a task of what to do, and a hint, and essentially you'll have to write your code on the right hand side. And when you run it, it will run through some checks, and it will go through some test cases and let you know if things are working as expected. When you're working through these problems, you aren't necessarily connected to us. So what you can do is, the other part of what we're doing is we do have REPLIT. So if you go to ycsx.org/WYSREPGen, it should bring you to a login for REPLIT. Now, you probably don't have an account yet. That's okay. In the lower left-hand side, do a sign up. And again, you can use your Google account, which is pretty convenient. I don't have this logged in right now, so you won't be able to see it all. Let's see if I can actually just instead create a quick username. You'll have to use a valid email address. And a pretty strong password. And then just click sign up. And what should happen is it should immediately bring you to our space for WySTACK. Go ahead and click on Start Projects for basic concepts, because that's where we're at in Solo Learn. Accept the permissions to enable notifications. And you'll notice that you have here also a new environment. If you click Run, you'll see a little print 0 here. Now, whatever code you write in Solo Learn, let's say you're struggling, you've done this over here. And you want help. Solo Learn, like I said, isn't connected. So what you're going to do is you're going to copy paste your problem, which will be very different for all of you. You're going to copy paste it up in here. Make sure that you put pound signs in front of it. And on the right, you're going to copy your code and also paste it here. So let me do this process. I'm going to copy the problem. I'm going to come over to Replit, and I'm going to paste the instructions here. And like I said, the one thing I need to do is I need to make sure that I comment out all of these lines of code. Well, they're not code, but they're lines of text. I don't want it to act as code. And a pound sign basically tells Python, hey, this is just a note. This is not actually code. Don't do anything with it. So now, why this is useful is when you are here, we will be able to help you. Right? So anything you put in Replit is something that we will be able to chat and talk to you about. You'll be able to write comments, questions, and we'll be able to engage with you in your code. So with all of that, let's go back to this. This is your task. Going over to Solo Learn and completing the first 2 units, using Replit as a space to put your problem challenges so that we can help you. I know this video was a little bit longer than usual. In the future, these are going to be about 10 minutes, and they're going to focus in on specific aspects of programming and how it relates to other things within computer science. So with that, if you have any questions at all, please don't hesitate to ask and reach out anytime. Thank you.